Hello, everybody. If you're joining us, we'll be starting momentarily. Welcome. We'll start just in a moment, allow people to join on. So if you can bear with us for a moment, people are jumping on as we speak.
All right. Thanks for that, Frank. And we'll probably just give it one more quick minute to let everybody kind of pile in. Make sure you don't run into anybody as you join. And we'll just give you just a second here before we introduce our guests and get things started.
Thanks, Sean.
How are you guys?
Very good.
Excellent.
Glad to be here.
Thank you.
Excellent. All right. So I'm just looking, our participant numbers are still climbing. We had, I think, well over 80 people sign up today. So that's great numbers. Just trying to make sure there's plenty of room. So everybody make sure you come on in and then we'll jump in here. So just to give another 10 seconds or so and then we'll jump in. Doing a countdown in my mind. All right. Seem to have flattened out. So let's get started. My name is Sean Casemore. I want to welcome everybody today to this special presentation in our What's Next series. Now, I would be remiss if I didn't tell you we've got some exciting things planned coming up in October for our What's Next series. So stay tuned. There'll be more about that in the newsletter that you'll see coming out shortly. So just watch for that for our next event and some pretty exciting things happening. But appreciate everybody joining us here today and wanted to take a moment just to introduce our guests and then we'll jump right into today's topic. So we have both Amir and Jonathan joining us. Now, Amir is a researcher in aerospace manufacturing technologies and has been with NRC, so the National Resource Council, right, of Canada, since 2019. His research focuses on collaborative robotic applications related to manufacturing processes. And obviously the dynamic and statistic modeling of robots. So quite a plethora of information relative to robots, cobotics, and we'll be able to discuss today how some of these applications are being applied in manufacturing facilities. We also have Jonathan joining us, and Jonathan is the team leader for the computer vision and graphics team in NRC's Digital Technologies Research Center, and he's also an expert in 3D imaging. So again, there's a lot of credentials for both these gentlemen that I would not do justice to read, and I know that everybody joining here today is really just trying to understand more about, obviously, robotics. You know, that's been around for a while, but cobotics is something that's very interesting. So gentlemen, I'm going to turn it over to you. And what I'll mention just before we begin, there is along the bottom a chat box and a Q&A. If you have questions throughout this program here this morning, please use the Q&A. Now, I'm going to watch both, okay, and we'll have a Q&A at the end here. But if you use question and answer, then as we answer it, I can check it off, make sure we cover it. Sometimes in chat, stuff gets buried. So for those joining us, you have questions, use that Q&A box. If you get stuck, you can always use the chat. We will have Q&A at the end. And again, with that, I want to turn it over to Amir and Jonathan. Thank you, gentlemen, for joining us.
It's a pleasure. So I guess I'll start by sharing my screen. There you go. And we'll go in presentation mode. All right. So everybody should see the nice PowerPoint. So thanks a lot for having us. That's the first thing I want to say. It's really a pleasure to be given this opportunity and to be able to talk about cobots in this context, because that's something that we, Amir and I both are quite passionate about. Today's session is going to be introductory, so we'll try to make to do our best to make it accessible for everyone. So if you do have more specific questions, don't hesitate. Either we'll answer at the end in the Q&A portion, or we can even take it offline if it's a lot more specific. Anyway, so I'm getting ahead of myself. The first thing I wanted to do was to give just a little bit of context. So Amir and I are both researchers at the National Research Council of Canada, and it informs how we look at cobotics. So NRC is it's the largest federal lab, so it's a big pool of highly qualified personnel in many fields of science and technologies, and we have quite a few mandates or roles to play. The first one, probably one that everybody here is familiar with, is to serve the government for a lot of science-related federal policies. For instance, maintaining standards for Canada, or updating the construction codes. That's also something that falls under NRC's responsibility. But we also have the mandate, the role to advance knowledge and technology. So we do a tremendous amount of research in many fields. And lastly, but well, it probably is what is on the most important in the minds of many of my colleagues, is fostering innovation in industry, helping Canada's industry to adopt new promising technologies and to really foster this innovation environment. So NRC is between 3,000 and 4,000 highly qualified personnel in many different fields. We cover things as broad and diverse as coastal, river, and ocean engineering, astronomy, aerospace research, AI-related research in my research center in digital technology. So it's a very broad number of topics, which means that it is relatively easy at NRC to have meaningful conversation in multidisciplinary for multidisciplinary projects or field. And that's how Amir and I got to know each other and to work together. So as Sean was pointing out, Amir is from the Aerospace Manufacturing Technologies Center, and he's an expert in robotics and cobotics, and he's been working on this field for quite some time. And we got to meet, and I'm from the Digital Technologies Research Center, who we focus more on AI, computer vision, and a lot of purely digital topics. And because we're at RC, we had many opportunities to get to know each other and our expertise. And because my team really focuses on 3D imaging, it's really complementary to what Amir's team was doing. So yeah, here is how we got to work together. And it also informs that we're here today with two different viewpoints on cobotics, and I hope that's going to be helpful. All right, let's dive into really the subject matter of the day. So cobotics, what is it? For those who did not guess it, the term cobots comes from the contraction of collaborative robots. There's not much more to say about that. I'm sure we could discuss etymology more if we wanted, but anyway, let's not lose time. So cobots have, in the last few years, become a very trendy topic. It received a lot of attention. And to me, that's sort of a threshold between niche science and technology topic that really interests engineers and researchers, and what's more mainstream is everybody's got a different threshold. But to me, once it reached the economists, that's where in my mind, it's starting to be important to communicate to a broader audience about what it is and what it is not, because there's a lot of potential, and there's also a few misconceptions. So physically, in practice, what are cobots? They're nothing special. They're made of building blocks from the mechatronics field, so either robotic arms or mobile platforms, usually combined with sensors. Typically, you'll have a few sensors on the robot themselves, and also for most industrial application, you'll want to have sensors placed in the environment or the work cell to sense what's going on. It's expected in cobotics that there is some intelligence behind the way that the robot interacts with human, and that this intelligence helps achieve a given task. And the last point, but probably the most important, is that there is a large focus on safety, and that's what it's at the forefront of the marketing campaigns of most private sector firms who have cobotics products. And we're going to come back on that, but just want to say that because products are designed to be safe, doesn't mean that you are using it safely. So that's something to keep in mind, and it's very important. All right, here I have a few selected applications that are of great interest in the research community. So I'll share that with you. Let's start with the first one here. Just cut the sound to speak over it. So here is one of the one of the most interesting uses that is very practical for industrial application. It's collaborative assembly. So in a case like that, you have a robot that provides components to a qualified technician that needs to assemble something. And the robot has to provide the different components at the right time and select the right components for the right product that is being built. So there is quite a lot of intelligence that can be built in that process, but it's one way that cobot can be tremendously useful. I'll pause this one. Just give me a second. Okay, so next one, we have another application of cobots that is called co-carry. So one thing that cobots could do to be useful in a industrial setting is to share the load of an effort that's being made by a worker. Now, in this example here, the demo object seems to be quite light, so it's not like the worker is in grave peril, but nothing prevents the load to be much bigger and to help a worker carry loads that are either heavy or awkward, and to do that with a lot of adaptability. In this case here, there's even EG sensors that trigger on the muscle activity, so that there really is a feedback mechanism that is customized to the worker. All right, let's pause. And a last example is what we call co-manipulation. So here you have a task that seems to be a bit difficult for the worker, but the robot can help take some of the load and progressively learn what the task is and how to do it with the guidance of the human. And progressively, the human has to provide less and less energy of effort. So it's a great way to reduce potential repetitive strain injuries or just to gain productivity in general. So in these three cases, I think those are nice ways that cobots can be used in ways that really are good for everyone's imagination in long-term thinking. However, the way that the interaction between the human and the robot are done is quite complex. So these are very exciting for the academia, but there are other applications where you have, where you can deploy cobots with simpler interaction patterns, and in which it makes a lot of business sense to do that in today's factories or shop floors. Here, there's 7 applications. Of course, I'm not going to go into as much details, otherwise it would take too much time, but let me just mention, for instance, machine tending. Well, that would be this example here. It's a very, could be a very simple way to use cobots, and one that takes advantage of the nature of cobots, where you have torque sensors and different features that make them more safe. So you don't have necessarily to lock them behind cages like you would with other robots. So it saves a lot of footprint in your assembly line. Collaborative assembly, we've seen an example on the last slide that was quite complicated. You can already deploy scenarios that look a little bit like that, some less complicated, but again, the idea is to have the robot help in the assembly of something where the human still needs to be in the loop. What else? Welding. Welding is a big topic as well. Here you have, I believe it's painting. And what else? One way, and maybe that's because of my background in computer vision and in imaging in general, but one way that cobots can be really useful, really fast, is in moving inspection sensors and do quality control. That's something that, it's the first thing that we implemented in our lab, because, well, as I said, probably a lot of the reason behind that being that that's a topic that we care deeply about, but cobots are very well suited for that. There you go. So, oh, sorry. So if we summarize a few of the opportunities and the challenges, so cobots are relatively cheap if you compare them to other industrial robots. As I said, footprint can be quite small. You don't have to lock them behind cages in most cases, which make the deployment easier. Generally considered safe. That's quite a defensive way to say it, but as I said in the introduction, they can be safe, and if you use them well, they are. One nice thing about cobots, because they enhance humans, they enhance what the workers are doing, and they maintain the engagement of the workers. Their social acceptability is usually high. People are quite interested to work with cobots. It's even in a lot of cases, people not only accept to work with those, but they really actively want to engage with cobots, especially for workers that are a certain age in their career, where they really want to get to learn new tools. Ergonomics, you can make great gains. One advantage that I would never have believed to say in a presentation if I had to guess 2 years ago is it makes social distancing easier. It makes some jobs that would really take two human workers breathing in each other's face into a one-person job. So it's a nice benefit. And lastly, it's relatively easy to fine-tune the level of complexity of your cobotics application. So you can deploy an application where it's very procedural, very a low level of interactivity, but still is very useful, to deploying a solution with modern AI that drives all the interaction and accomplishes very complex tasks. However, in those cases, you do need to have access to a lot more data and to a lot more expertise. So sometimes having access to that talent is a challenge. Most time, I would say, if I'm being completely honest. Another challenge that mirrors some of the opportunities is safety certification and acceptance. I put them together. Every organization has different guidelines and a different level of risk tolerance and a different preconception of what robots, where robots stand in this spectrum of risk. And it is a challenge to move the needle for an organization, whether it's coming from a place where cobots are, or robots in general are considered relatively dangerous and has to be managed with a lot of attention, to a spectrum where it's the complete opposite, where people might be tempted to say, well, these are cobots, these are safe, and we don't have to do nothing. But it just requires communication and a champion that really is willing to put the energy to address those and to talk to everyone in your organization. And well, last challenge, this one is maybe, it maybe relates to almost all new technologies, but there's not a lot of people who really understands what can and cannot be done at the moment with the tools that are available off the shelf. And those that offering changes every day. So it's quite understandable. But in that context, defining what the right requirements are for an application is quite difficult. All right, just want to point out that right now we're in a great space where there is a lot of products that are commercially available for cobotics applications. I'm not going to go in details and list every one of those. It would be silly and take way more time than what we have available today. But there's a nice inventory on Cobotics World that it might be a good place to start if you want to browse through a few of the products. What I can say for my labs, the labs that are very close by in collaboration centers that we have with universities, is we do have universal robots and also a Kinova arm in the labs where we develop applications. Although the Kinova is not technically marketed as a cobot, so you have to be very careful. But they have nice access to very low level control of the robot that make academic applications and development quite easy. So in both cases, we've been quite happy. All right, and now I'm going to switch over to Amir. We're going to look at an application that we're just starting to tackle at the NRC, and because we're starting the initiative, all the questions that you might have related to cobots, how to what matters, how to deploy it, how to structure the effort. We're going through that right now. So I'll let Amir talk to those points more in detail. So the floor is yours.
Thank you. And hello, everybody. Jonathan explained some current collaborative robot application and research activities on this field. He talks about NRC. I just want to mention that we're not an integrator. We just try to bring the low-level TRL solution to a TRL 5 and 6. And after that, we rely on Canadian companies to industrialize the developed solution. Now we'll go to a recent project at the NRC. What you will see is a part of feasibility study of the project, or let's say preliminary phase. The main project starts this month and lasts for 3 years. And we would like to address technical issues for a collaborative finishing process. Then, as you know, in manual finishing process, we have lots of flexibility, fast setup at low cost, and visual inspection can be done by the operator. However, the manual finishing operations are long, non-repeatable when between different operators, and causes ergonomic disorders. Next, please. The conventional automized finishing operations are faster with constant quality and reduces musculoskeletal disorders. However, they are costly and need high level of effort to industrialize in terms of tools, programming, and characterization. They're also not very flexible when a part geometry has large variation. And therefore, they require a good quality control of input condition. Next, please. And recently, we see more commercial solutions for collaborative sanding and polishing, which are good for cycle time, quality, and to reduce musculoskeletal disorders. But they are not yet ready for complex geometries, and they require offline or manual programming. Next, please. Yeah, in this quad chart, we position the finishing operations based on 2 criteria, productivity, which is the horizontal axis, and flexibility with respect to cost and capital investment, which is the vertical axis. We can see manual operations are low cost, more flexible, but they are less productive. In contrary, conventional robotized solutions are productive, but not so flexible and are expensive. And the existing cobotic solution is in between. We target the upper right corner to enable cobotic. Click, please. And another, yeah, good. To enable cobotic solution with higher techno-economic impacts to be more affordable, flexible for geometry variations, with a fast setup for new parts, and of course, collaborative to keep the operator in the loop and benefits from his knowledge. Next one. Within long discussion with our clients and partners, we develop our vision for a cyber-physical system integrated to a collaborative platform. A cyber-physical system, or CPS, is an intelligent system composed of many modules to interact with the robot and the operator, and to provide many tools to make the operator's task easier. In this CPS, we consider a digitization module. Even that nowadays we have the 3D model of a part, digitization with a structural light is necessary to create the real 3D geometry of the part as it is built and with all variations and distortion. We also need a module to manage the process parameters. Therefore, we create master charts which are a result of process characterization to suggest process parameters to the operator. In the meantime, in parallel with artificial intelligence, AI. We will learn from operators' feedback on the achieved quality, and later the CPS can suggest the best process parameters for a desired quality. The core of CPS, as you can see in the middle, is the interaction with the operator via touchscreen and gesture recognition. Once a task is defined, the core determines the best finishing scenarios, creates the best optimum robot trajectories by, of course, avoiding collision, and it indicates the required setup via augmented reality. Once everything is verified by the operator, the program will be sent to the collaborative robot to be executed, and the operator can verify the quality during and at the end of the task, and can impose additional passes to achieve the quality. His feedback also will be used for machine learning. To ensure that the cobot is able to apply a constant finishing force, it will be equipped with a compliance head. In the beginning, we use a passive commercial compliance head, and we develop an active multitask compliance head during this project. Next, please. Okay. Now let's look at the typical finishing process within this vision. I present you an imaginary scenario, but with all different modules of this platform, the CPS. Other scenarios or other ways to perform a finishing task can be imagined. Of course, this case is for a new part, which needs to create setups and create everything. But if once you have a part already programmed, then you can just load the same programs and use it many times as you want. Then first, the operator interacts via touch screen with digital twins. By this, I mean 3D model of the part and digital mock-up of the platform. He selects some geometrical features and assign finishing tasks and tools for those features. Using gesture recognition, the interactivity also can occur directly on the part. For example, the operator can divide a finishing task into 2 tasks or limit it to a portion of the surface by his gesture on the part. To specify process parameters such as advance and downfeed, the operator can rely on his expertise or on master charts, which will be integrated to the CPS, and they are result of process characterization. Of course, during this project, the CPS improves its intelligence via deep learning and can suggest best process parameters for a desired quality. And by this, I mean neither over quality nor bad quality, because for each of them, there is an extra cost. Next, please. Then the CPS generates the best finishing scenarios. We will develop optimization algorithms using the robot redundancy to determine the best position of the part on the table and to reduce the number of setups. In addition, the CPS plans work sequences and clamping if required. It creates optimum robot trajectories free of collision, and therefore this way we eliminate or reduce the need for offline or manual programming. The integrated scene supervision camera and augmented reality projector will help the operator to position the part correctly on the table and to clamp it. And the goal here is to eliminate the conformation jig, which are expensive tools, and they are used to shape the part to its nominal geometry. Next, please. The CPS will also be equipped with a structured light camera Vision algorithms will be developed to scan complex parts with reflective geometries. The objective here is to have an affordable, precise, and fast system. The scanning program is on CTS side that will generate it automatically based on vision system requirements. And at the end, the generated point cloud would be treated to establish the real model of the part with all non-structured features. For example, for welding, we can think about weld seams, weld spatters, and also for other parts, for machine parts, we can think about burrs, and as well as deformation caused by clamping. Now, Jonathan will explain more about vision system and challenges. Thank you.
Right. So one of the challenges that we face in cobotics application is how you use vision. And again, I'm heavily biased, so you are going to have to take my word for it. But in this case, and in many industrial applications of cobotics, you have more than one level of 3D imaging level in your application. Here you have the component itself that you want to inspect for determining the right quality, and you also have some scene supervision where you want to be able to infer what the worker is doing and to have some level of interaction. All right. So the most common type of sensor that people know to, especially to interact with the humans, are RGB cameras. So I want to touch base on that and to open the box a little bit, give you a sense of what are the major flavors of technologies that are used, because it does inform your choice and they all have different challenges. So RGB cameras, what they are, or what they provide you is a color, so RGB, sorry, and a depth for each pixel. They can measure the depth in different ways. The most commons are structured light, active stereo, and time of flight for this family of sensors. Active stereo is a technology where you have two cameras that will do synchronized captures. And there's a stereo matching process that will match a pixel from the right camera to a pixel in the left camera. And by triangulation, you're going to have 3D points. Now, the active part of active stereo is usually there is an additional projector in the unit that typically operates in the near infrared, so a human would not see it, but it projects a pattern that looks semi-random to add some texture on the scene. And so those are quite nice and relatively immune to motion artifacts because you have one synchronized capture. Structured light, by contrast, you have typically a single camera and a projector that you use to show multiple patterns that you use to decode what depth is associated with each pixel. So that means that you need to do multiple captures, and it takes more time. And because of that, it's a little bit more vulnerable to motion artifacts. At the same time, it is also typically easier to achieve higher accuracy and resolutions with those. And lastly, in the last few years, we have seen quite a few time-of-flight sensors that are becoming less and less expensive. Those used to cost a big amount of money, but now there's a few cases where they are mass-produced. and where they are cheap enough to be considered. And in this case, there's no triangulation. Really, what gets measured is how much time the photons that are emitted by the device take to go from the device to the scene, interact with the scene, and come back to be measured. And so this requires quite specialized electronics to be able to do that. But the specific flavor that is cheaper these days is continuous wave time of flight. And in this case, you need to, you basically measure a phase shift in a signal that you send. Without getting too technical, it shares a lot of similarities mathematically and also in the type of artifacts that you'll see with structured light, although the devil's in the detail, and you really need to test out the technology that you plan on using. So just to reiterate what I think are the most important things to get in to keep in mind when you design your application. Of course, accuracy, resolution, and speed of capture are something that you should look at, but that's the most evident one. I don't even have a slide for those because I thought that was self-evident, but motion artifacts, even when you have enough frame rate, they can manifest themselves with either wavy 3D structures or just noise in general in the capture. And it's really important that you validate that you are okay with the type of artifacts that you might see for a given application. So if you have a robot that moves fast with a sensor on it, you might see a lot of motion and you need to choose accordingly. And on the other hand, if you want very high resolution and accuracy and you're okay with stopping, then something like time multiplex structured light might be okay. And other type of problem that you will see with 3D imaging in the in industrial applications of cobotics is related to multiple reflections. So most 3D sensors are the commercially available ones, operate under the assumption that you have light coming from the sensor to the scene and back to the camera and the sensor. And there's only one interaction with the scene. If you have multiple interactions, so say multiple reflections or penetration, subsurface penetration in a material, then this assumption is no longer valid and you will have quite interesting behaviors. And by interesting behaviors, I mean useless points. But there are ways to go around that. Here, I do just a little bit of shameless plug. That's a method that we've developed in my lab to compensate for multiple reflections and to filter it out. So there is a way, or there are ways to make yourself less vulnerable, but it's very important to keep that in mind, especially because typically this will happen in areas of high curvature in concavities, and it's often where you see the most defects. So that's where you would like to have more points and higher quality imaging to be able to spot defects. So all the more reasons to be very mindful when you develop your application. And last thing I want to say about 3D imaging, I've talked about some of the methods to do 3D imaging and the ones that are available in nice, well packaged products right now. If you need to go to high resolutions or to very large objects, say you want to deploy a cobotics application where you need to track robots on hundreds of meters, There are other sensors and other ways that this can happen. And if you need to look at defects that are at the nanometer, well, let's say beyond the micron, there are ways to do it. But it could be a whole tutorial by itself, so I'm not going to dive into details, but I just wanted to say, if you come in into problems there, that's the bread and butter of my team for a while. That's something that we know very, very well. So if you need advice, don't hesitate to contact us, and we'll be more than happy to have a conversation. All right, back to Amir.
Thank you. Good. Now back to the process. By having a good 3D model, a realistic one, and based on this model, the cyberphysical system in interaction with the operator calculates the number of finishing passes. The operator can verify the robot trajectory in simulation, and if everything is satisfactory, authorize the execution of a finishing task. We said that we know the real geometry, which is helpful to calculate the number of finishing passes, and also for the robot to follow the real geometry. But it's not really practical to adapt to each and every small deviation of the geometry, since the robot cannot react very fast. Then it's common in robotized finishing operations to use a compliance head. Currently, our platform is equipped with commercial available radial and axial passive compliance heads. Each head can provide compliance or compensation in one direction by applying a constant force to the part. And during this project, we developed an active compliance head that will be modulable and programmable and can provide and or block the compliance in different directions. Then this way, we won't need to change the head for different applications. We can use the head that will develop for all the different applications. And in line with a smart factory, in this project, information of such as, for example, task progress, the percentage of completed and remaining tasks, as well as the status of the platform are available to the operator and to the different stakeholders. Next, please. Yeah. Once the finishing tasks are completed, the operator will inspect the surface quality and give feedback to the CPS using touch screen or gesture recognition. Jonathan research team are working to use the structure light camera for quality measurement. This way we'll have an automated and more repeatable way for surface quality measurements, and the result of this measurement can be projected on the corresponding surfaces for the operator to accept or reject, or to launch extra finishing passes. And the data concerning the surface quality, the tool, process parameters, and robot trajectories are all gathered and saved and used for training of a neural network. And this will allow us to capture the operator's knowledge and learn from different platform experiences. And later, the system can help less experienced operators to define and perform good quality finishing tasks. Next, please. Here you see a photo of our platform in Montreal. There are many systems that are attached to this platform. I don't have the time to go through all this, but I want to talk about safety and security devices. You can see that we put, not yet. We can put emergency stops in both sides of the robot. We have also air skin, which is air cushion, which covers the robot and it gives more sensitivity to the robot. In the case of the contact, the cobot can stop faster. From process side, we also evaluate some process hazards. And we put a downdraft table and a scrubber, which is behind the platform, to collect the dust of finishing operations. By the way, we have not yet do a risk assessment, and the risk assessment is coming very soon. Now, next, please. Okay, talking about the safety. These type of robots are designed to ease the collaboration between robot and humans. Different person in an organization may think of this robot differently. Some think that they have to put it in a cage, then they are useless. And some think since they are collaborative, there is no need for any safety consideration. The fact that a robot is a collaborative one doesn't mean that the whole cell or the operation is safe for human. We have ISO standards, ISO 10218. Part 1 covers the requirement for manufacturer of industrial robots. And please note that the cobot is also considered as an industrial robot. And part 2 of ISO focus more on integration and installation of robot and all attached system. We have also a Canadian standard Z434, which is equivalent to ISO 10218. And there are some technical specification or technical report which are not yet part of the standard, but they will become standards soon or late. We have on ISO side 15066 and on NC side RIA, which is Robotic Industries Association, technical report 15606 that describes more collaborative operations. But keep in mind that this technical specification is in support of ISO 10218. It means that you have to interpret them as with ISO standards. Now, please, next. In a collaborative application, we may face hazards between the application and the environment, the end effector and the tool, and other system and machines. Therefore, each case is unique, and we shall do a risk assessment for each item to identify hazards and to eliminate them. Each risk must be evaluated based on its severity, exposure, and avoidance to establish a risk level. That is what you see in table 2. And as a function of risk level, in table 4, you can see a risk reduction measures or many risk reduction measures must be considered. For example, if we have a high risk level, absolutely we have to consider reduction measures from elimination to safeguarding. In most cases, there are integrators who realize robotic application, thus they shall perform a risk assessment. But nowadays, we can see end user buying collaborative robots to implement them in different situations, since they are simple to use and set up. Therefore, in this situation, the responsibility is on the end user to perform the risk assessment. Next, please. Yeah. There are 4 different types of collaborative operations, such as safety-rated monitoring stop, hand guiding, and speed and separation monitoring. These 3 can be used with big industrial robots. Collaborative robots themselves are originally designed with power and force limiting, which is the 4th type of collaboration operation. A cobotic platform, which has end effector tools or other system, can use a mix of all these collaboration types. Now, bear in mind, when the operator is inside the cell, contacts that could be quasi-static or transient could happen either intentionally or unintentionally. But the force or pressure, whichever, is more critical, must be limited to avoid any harm to the operator. And this is true not only for robots, but also for the end effector, the tool, and the parts if it is moving. In the right figure, you can see the force and pressure limits in transient and quasi-static contacts. This limit for each body region, and we have a total of 29 defined regions, are different and are listed in technical report. And also the technical report specifies that no contact is allowed with the head and the neck. Therefore, the robot program must avoid those regions. The contact pressure and force must be evaluated for each case of contact, and if not respecting the limit, corrective action must be considered to alleviate the risk. Next, please. Now we watch together a demonstrative video, which is the result of feasibility phase of this project. For the time being, there is no vision system, and the interface and the cyberphysical system will be improved and modified during 3 years of the project. You see here that we load the platform, and takes a little bit time. Then we select features interactively with touch screen. We define a task. We're going to find all tangent curves. We define a task with a tool associated. And we define some parameters. Then we generate toolpath. And generate task. Generate a sequence, and then generate the program. The program we can see in simulation, and we can see also the joint variation during the trajectory. Since we don't have much time, we can go to the next one. Yeah, and here you see the grinding task that was defined within the CPS, which is executed synchronized with the CPS. In the meantime that you're watching this video, and as a conclusion note, thanks to be there and listen to us. I hope that you enjoyed from this webinar. We try to give you an insight about collaborative robots, the current and future application, the opportunities and challenges. We showcase our Cobotic project to illustrate the extension of collaborative application to more demanding manufacturing process, as well as interactivity, vision, and scene supervision. The idea here is to use the best of a collaborative robot with the knowledge and expertise of an operator. As Jonathan mentioned, the NRC has many experts who can work together to solve your industrial problems. In this case, you can contact us and we'll be happy to talk to you. And at the end, I insist again on the importance of risk assessment when you use collaborative robots. Thank you all.
Great. Well, thank you, gentlemen. Actually, I'll direct you. There's a question from, looks like Harv. Sidhu, he's asked for your contact information. He had to jump, so I'll let you, he's given his email. I'll let you follow up with that. There was also a question I noticed, Amir, you answered from Gail relative to Canadian manufacturers. It sounds like Kinova is about to introduce a cobot soon. So more to come on that. If somebody then, as you know, who's joined us here today, wanted to see a cobot in action, would they reach out to yourselves to see if they could arrange a time to come to your facility?
Of course.
Yeah. Okay. So that's open with the contact information everybody sees on your screen. If you'd like to see this in action, and that video you shared was in your facility, was it not?
Sorry, I didn't hear the question.
Sorry, the video that you shared at the end, was that
Yeah.
of the cobot that's in your facility?
Of course, of course.
Yes. So for those who are joining us who actually want to see a cobot in action, touch, feel, see how this works, you can reach out to either Jonathan or Amir and arrange a time to visit when it's appropriate.
That will be our pleasure to meet them and to show them our facility.
Excellent. And then I noticed there's also, there was a question here relative to the PSHSR procedure. If you see in the chat box from Christina. So to ensure a cobot follows all safety guidelines, does it follow the same PSHSR procedure as an industrial robotics cell?
I'm sorry, I'm not an expert on safety and security of the robot. This one, PSHSR, I'm not aware of that. But again, they have to follow the ISO 10 to 18, and this one I'm not aware, but we can discuss later on that.
In general, if I can add, the fact that you have something that's called a cobot does not give you an exemption to do anything, unfortunately. So you have to consider all the measures that you would take normally. You have to at least consider them, and those that do not make any sense in the risk assessment, you'll be able to take mitigating actions. But unfortunately, having a cobotic application, it's not a waiver.
Okay. All right. And then
yeah.
Angela.
And just to add that, since that is an industrial robot, we have to follow all the requirement of ISO, because it's considered as an industrial robot. Even that we say that is a collaborative one, then we have to follow ISO standard.
Okay, great. And Angela has put her contact information in the chat box as well. If you can grab that, she'd like a copy of your slides. So gentlemen,
Yes.
Thank you very much for your time. This was, I had an idea of what cobots were coming into today. We went very deep. So hopefully those who joined us really have a full understanding of not only obviously what collaborative robots are about, but how they can be used and applied, and how they're going to become or continue to become more popular as a source of almost complementary labor in a way, or to complement labor for manufacturers across Canada. So thank you very much. You've shared your contact information. Thank you to everybody who's taken time out of your busy day to join us here today. If you have any further questions, you can always follow up with us here at NGen. You can take the registration email and simply reply to that if it's easiest. Or you can reach out to myself directly, sean.casemore@ngen.ca. Gentlemen, thank you again for your time. Thank you, everybody, for joining us. And until next time, we'll talk to you then.
Thank you so much.
Thank you, everybody.
Thank you.
Bye-bye.
Bye.